Okay, hello everyone, and welcome to today's lecture. I have my slides again, and hopefully every can see the screen and hear me clearly. And hopefully you don't hear the background noise. If you are hearing this disturbance, sorry for that. Uh, okay, so last time we were talking about jump and call instructions, right? Uh, Okay, before I think I start the lecture of today, I'll give you a recap of what we did last week. Uh, just remember that we have the midterm exam uh, scheduled on what date? Let me check. I think it is, yeah, it is next Monday, right? Coming Monday. So 14th of October. And in next class on Thursday, we will do a practice exam for midterm one. Okay. So keep that in mind. And I will make an announcement on the canvas regarding details of the or logistics of the exam. But just keep in mind that it will be in person. It will be uh, it will be held in the classroom, which is booked for our class duration or for our lectures, right? I will give you the uh, uh, room number of the class, right? And also the duration. So you can, the announcement when I will make it, you can go there and check all the details. But just keep in mind that it will be in person, not online. Okay. So last time we were talking about jump and call instructions, and we had a look at different instructions in those groups, like for example, jump, relative jump, and indirect jump, and then in call category we had instructions of like call and then relative call, uh, indirect call, and extended indirect call, right? So today we are going to actually, I was supposed to cover this subtopic time delay in the last lecture, but I couldn't complete it. So let's go through this and then we will move on to the next topic, which is about shift and logical instructions or so logic instructions in AVR assembly. So time delay. So basically the thing is like if we want to insert the time delay, or we want to wait for some time before we go ahead and continue executing our assembly code, how can we do that in assembly? So how can we implement the delay? So you have already seen examples of doing that in the labs, actually starting right from the first lab. So you must be familiar with that, how you can implement the how can you implement that delays? It is basically nothing but just the loops where you are simply wasting the time by iterating the loops multiple times, right? So so we will go through some examples, and the other thing which we'll focus on in those examples is that how can we calculate the time which is consumed by a delay routine, right? So uh, so here is an example. So it is not the example about delay, but it is just an example basically about trying to give you an idea or trying to give you a concept that each instruction, when you execute it on a microcontroller or a microprocessor, it takes finite amount of time. And the amount which is taken by an instruction, it basically is measured or specified in terms of clock cycles, right? Are also known as instruction cycles, like how many cycles are consumed by an instruction, right? So most of the instructions in AVR microcontroller, they actually take only one cycle. There are some instructions which take more than which take more than one cycle to complete, more than one clock cycle to complete. And at the end of the book where you have this table, at the end of your textbook where you have this table in appendix giving you all the instructions, it also specifies, sorry, it also specifies the number of cycles that are needed for completing each of the instruction, right? So for example, here in this code snippet, we have five instructions. Three of them are load immediate and one is add, right? Let me select the pointer. Okay, so if you like look at that table at the end of at the end of the book in the appendix section, you will find out that each of the load instruction, it takes one cycle to execute, and same is the true for the add instructions. So if you have a program with these five instructions, so it means that in total 5 clock cycles will be needed to complete execution of that program, right? Uh, so the purpose of this slide is just to let you know that every instruction takes a finite amount of cycles to complete execution, and for most of the instruction in AVR assembly, it is only it is only a single clock, right? Now let's have a look at this delay routine. So here, what we are basically doing is like we are loading. So we are actually executing a loop 100 times, right? We are loading the loop counter 100 in a register R16, and then we are saying okay, add R16 to R17. Maybe before here we have already initialized R17 with some number, right? And then we are saying okay, decrement R16, so it will become if it was initially 100, now it will become 99. And then we are saying branch not equal again. So if the result of decrementing is not equal to 0, so then go back to the loop, right? To go back to the label, so there is a loop, and this loop will be iterated how many times? 100 times. Now let's have a look how we can measure or how we can calculate the time which will be needed to complete this code snippet. So if we look at the instruction table, which I mentioned earlier, you will find that load in immediate instruction takes only 1 clock cycle. Same is true for add and decrement. However, your branch not equal instruction, it may take 1 or 2 cycle, depending upon whether the branch is taken or not. Why? Let me try to explain. Hmm. Yeah, just give me 1 minute. I need to connect the drawing pad uh, with my computer so that I can use the OneNote. Just give me 1 minute. Yeah, and when I'm looking at this OneNote, it reminds me of a question from a student that can I embed it on Canvas or not? I will try it. I mean, I forgot to do it last time. Okay. So today is week 6 and sorry, week 7 and day 1, right? So, so here in the slide, I'm claiming like for branch instruction, the execution will take either 1 or 2 cycles, depending upon the upon whether the branch is taken or not. So what does it mean? Why? How we? What is like logic behind our understanding behind saying that it may take 1 or 2 cycles? So the thing is this, like in AVR microcontroller, you have so yeah. So you have your AVR microcontroller is pipeline processor, right? So pipeline processor means there are 2 stages, fetch and execute, right? And then execute is like subdivided into fetching the operand or reading the operand. Let's say it is named as R, and then processing the instruction. Like for example, if you say the instruction is add, so reading the operand will mean reading the 2 register, and then processing mean will adding the 2 numbers together, and then write mean the writing result back into the destination register, right? So the thing is like what they do is like since it is a pipeline processor, so it has 2 stages, stage 1 and stage 2, right? So what happens is like if you have, let's say if this is your timeline, right? Initially what happens that you have only one instruction. Let's say I'm naming it as instruction 1 in the pipeline, right? And let's say your program is sequence of instruction 1, instruction 2, instruction 3, And then you have like, let's say branch not equal, right? And you are putting a label, and I'm naming it as L. Let's say this is label. Yeah. Okay. So what is happening here is like in the first clock cycle, you will have I1 in fetch stage, and there will be no instruction in the execute stage. I'm writing F for fetch and E for execute. So in the next clock cycle, sorry, in the next clock cycle, so what will happen is like you will have okay. So let's say this was cycle 1, right? And then this is cycle 2. So what will happen that in next cycle, your instruction will enter the execute stage, and your so what will happen is like I don't know, I'm like if I'm drawing the figure correctly, but hopefully I will be able to explain the idea. So your instruction 1 will be in execute stage. I know the format of the figure is not correct, but let me simply continue using the same forward. So instruction 1 will be in the execute stage, and instruction 2 will be in the fetch stage, right? They are not in sequence. Like they are, how to say? I don't want to open the figure from the book, but okay. But I think you can understand that what I'm trying to necessarily say is that there are two instructions which are currently being processed. However, one of them is in the fetch stage, instruction 2, and the instruction 1 is in execute stage. And then what will happen in next cycle? Like, let's say this was cycle 2, and now we have cycle 3. So what will happen is like your instruction 1 is completed, right? It leaves the pipeline, because remember, pipeline is of only 2 stages. And then your instruction 2, it will go to the execute stage, and your instruction 3, it will be in the fetch stage, right? And then you will have in next cycle, what will happen is, right, let's say this is your cycle 4 now. So you have instruction 3 in the execute stage, and you have branch not equal in fetch stage, right? Now, remember what is happening. Instructions are going through the pipeline in sequential order, right? So let's say here I have another instruction which I'm naming instruction 4, right? So, and let me try to move cursor a little bit down. Yeah. So now in next cycle, what will happen that my branch not equal instruction, I'm only writing branch for that, right? Because it is true for any kind of branch instruction, right? So branch instruction will be in execute stage, and instruction 4 will be in fetch stage, right? Now, let's say that branch is not taken, right? If branch is not taken, which instruction will be executed? I4, right? The next instruction, this one. This instruction will be executed if branch is not taken, right? So which mean that we are fine, right? So we are fine in the sense that we have fetched the correct instruction here. We have correct instruction in the fetch stage, I4, if branch is not taken. However, if branch is taken, then what will happen? That we need to execute the next instruction, not I4, but we need to go back to the label L1 and fetch in the instruction I1, right? So let me try to draw that here. So let's say we are assuming that that the branch is taken, right? So now we don't want to execute I4, right? So we need to replace, we cannot allow I4 to enter the execute stage, right? So what we will do basically, we will smash it. Basically, we will replace it with no operation, right? So what we will do is like here instead of I4 in the execute stage, instead of I4, we will have NOP, and then in the fetch stage, we will have I3, right? So which basically mean that we have wasted one cycle. Why wasted one? Because we used one cycle to fetch in I4, right? We one cycle is needed to fetch in the instruction, fetch the instruction I4, but after fetching it, we actually I1 here, but after fetching it, as the branch was taken, we cannot execute I4, we must go back to the I1. So we bring in, or we fetch the correct instruction I1. So for that, this cycle is wasted, right? Because we converted it into NOP, right? So as a result, what happened that, let's say if the branch is taken, then only one cycle is consumed in bringing in the next instruction, next correct instruction. But if the branch is not taken, only one instruction, one cycle is consumed in bringing in the correct next instruction. However, if the branch is taken, so which was the case here, right? But if the branch is taken, we need two cycles to fetch in the correct target instruction, which is I1 here, right? So it's mean that now whenever the branch will be taken, this branch and any kind of branch instruction will consume two cycles, right? When the branch is taken. But if the branch is not taken, then it will consume only one cycle, because we need one cycle. If branch is not taken, we need one cycle to fetch in the correct instruction. But if the branch is taken, we need two cycles to fetch in the correct instruction. Sorry for that. Sorry. So, any questions here? Now, if I say that the time consumed by branch not equal instruction is either 1 or 2, so it should be, it makes sense to you. If you are still confused and if you think it is not clear, let me know. Everyone is clear? Okay. Okay. So this basically too comes from the branch penalty, because when the branch is taken, it's mean that we smash one instruction which was fetched in from the sequence. We cannot execute it. We need to replace it with NOP and then bring the correct instruction from the branch target. So that's why we have a penalty of one extra clock cycle. So making the time needed for branch not equal to 2 cycles, right? So how we can calculate the total time which is consumed in executing this code snippet, right? So for that, we first need to know what is our clock frequency. So let's say the clock frequency of our microcontroller is 16 megahertz, right? So then the time delay which is implemented by this routine is, we can calculate it by simply adding these numbers, right? So this one basically is for load immediate instruction, because this is executed only once. However, the instructions in this loop, they are executed how many times? 100 times, right? So we have we have 1 plus 1 plus 2. Why? 1 is coming from this add instruction, the second one is coming from decrement instruction, and 2 is coming from branch not equal. And why 2? Because we know, depending on the value of the loop counter, that this loop will be executed 100 times. So if it is taken 100 times, this means every time it needs 2 cycles, right? So 1 plus 1 plus 2 times 100. And then if it is the clock cycle is 16 megahertz, so what you can do is that you can, so it's mean that you need these number of cycles, right? You need these number of cycles, and one cycle is equal to what? Is 1 over 16. uh I I don't know how you read it. Is it million? So whatever. So 1 over 16 and then 6 zeros. So this will be, and then you can do the math. And when you'll do the math, you will find 25.0625 microseconds. So it will take 25.0625 microseconds to execute this code. So it's basically mean that you are implementing a delay of 25.0625 microseconds. Okay. Any questions? Okay. Now let's have a look at another example. Like for example, we have this routine again. Uh, so what we are doing is that we are putting 50 in R16 as a loop counter. And then in the body of the loop, we first have two NOP instruction. Then we say, okay, decrement R16 and branch, go back to loop if the result of decrementing R16 is not zero, right? So again, we first need to know the instruction cycle needed for each of the instruction. So load immediate take one instruction, all of them take one instruction, and branch not equal, as I explained, it may take two instruction, two cycles or one cycles to complete, right? And again, doing the math in the same way, you can find the number. So what this one is for load immediate instruction, this instruction, and then we have this three for by adding these three cycles, right? And this two for branch not equal, and times 50. Why? Because our branch will be taken 50 times. So in total, we will have this number of cycles, right? And one cycle takes 1 hour 16 and 6 zeros amount of time to complete. So you can do the math and you will come with the result 15.68 microseconds. Okay. Okay. Uh, Here we have another example, but the difference from the previous example is that this time we have two loops. Actually, we have nested loops. So let's see how we can calculate the time delay implemented by this code snippet. So what we first thing we need to know is like what is the what are the number of instruction cycles to execute each instruction. So for all of them it is one, and for branch again it will be one or two. If the branch is taken, it will be two cycle. If not taken, it will be one. Decrement instruction takes one cycle, and again we have branch instruction, right? So let's first focus at the inner loop, right? So this rectangle shows you the inner loop, right? So how many time is this inner loop executed? Re- Remember, we are decrementing R16. So basically it means that R16 is our loop counter. What is the initial value of R16? 50. So it is executed 50 times, right? And then we also have an outer loop, right? And how many times the outer loop is executed? Remember, we are decrementing the value of R17. So it's mean it is our loop counter and it is initial as with value of 20. So it will be executed 20 times, right? So what can I do? So if I first focus on like the outer loop, so this first instruction, load immediate, will be executed only once, right? Because it is used only to initialize R17 one time. But after that, we enter the body of the outer loop, and there we have load immediate instruction. So it will be executed how many times? 20 times, right? And then I will come back to L2 later on. So then we can move to the decrement instruction. It is also in the body of the outer loop. It is also executed 20 times. So we are multiplying with 20, right? So it will take in total, it will take 1 times 20 cycle. This will also take one times 20 cycles. And branch not equal L1, it will be executed. Uh, so will it be executed 20 times or 19 times? It will be, yeah, it will be executed 20 times, but remember, this is our not for loop. Basically, it is our do while loop, right? So it is do while loop. And in do while loop, what do? You don't check the condition for the first iteration, right? So that's why what happens like 19 times, what happens that your branch is taken, right? One is initial when you actually not checking the condition. One is that iteration. And for next 19 iterations, what happen is like your branch is taken. So in total, the loop body is executed 20 times. However, so 19 times your branch not, you are taking the branch, but you are going back to L1, right? But 20th time when you, after decrementing, you check it, what happens is that it is equal to 0. So what happens is that you execute the next instruction. So it takes branch not equal takes in that case only one cycle. That's why here we are saying that one time in one iteration it takes only one cycle, and for 19 iteration it takes two cycles, right? Any questions here before I move into the like inner loop? No? Okay. So now let's talk about the inner loop. So in inner loop, we have NOP instruction first. So the NOP instruction takes one cycle. However, it is inside the body of inner loop, which is executed 50 times, but inner loop itself is inside the body of the outer loop, which is executed 20 times. So in total, we will have 1 times 20 times 50 cycles. So this is how many cycles will be consumed while this NOP instruction will be executed, right? During the whole code snippet, whole execution of the code snippet. Same is true for the next NOP instruction, right? Same is true for the decrement instruction, 1 times 20 times 50, right? The only interesting thing is again this branch not equal instruction. Again, remember, first time we are not checking the condition. Since we are not checking the condition for the first time, we without checking the condition, we enter the body of the loop. So in total, yes, the body of the loop is iterated 20 times, but the condition is checked. The condition is true for 19 times, and one time it turns out to be false, right? Sorry, not 19 times, 49 times. Remember the loop counter is 50 here, right? So for 49 times, we have we spend 2 clock cycles because 49 times branch instruction is taken and one times it is not taken and it falls through to the next instruction. So it consumes only one cycle, right? So when you do the math by adding all these cycles, which is shown here, so then you will get the total execution time in terms of cycles, 5060 cycles, right? But remember, these are 5060 clock cycles. And then if you want to convert into the times or like into seconds, so you can simply, if let's say your clock frequency is, I'm just making up some number. Let's say your clock frequency is 1 megahertz. So what you can do is that you can divide it by one. You can simply divide by 1 divided by 1 raised to power 10 raised to power 6. Okay. So then you will get the result. Any questions here before we move to our next topic, which is about logic and shift instructions? No? Okay. So in rest of the slides, we are going to cover logical instructions, how they can be used to do the masking, and what is masking, rotate instructions, shift instructions, and then we will also talk about binary coded decimal numbers, right? And conversion between binary coded decimal numbers and ASCII, ASCII coding of a character. Cool. So I think in first or second lecture we had talked about the logical operations like AND operation, OR operation, exclusive OR, complement, uh, yeah, NAND, and so on. But we haven't seen yet the instructions which we can use to implement those operations, right, in AVR microcontroller. So we have a bitwise logic and operation. So what it does is that just like, for example, like add, if you specify 2 registers, their operands will be added. Similarly, in AND, when you specify 2 registers, their values are ANDed together, right? And there is also another variant which allows you to specify the second operand as an immediate number instead of a register, right? And here when we say bitwise, we will see examples, but when we say bitwise logic answers mean that, for example, in the first instruction, the uh, bit at index 0 of destination register will be ANDed with the bit at index 0 of the source register. So every bit in source and destination, they are ANDed together with the corresponding bit in the other register. Bitwise logic OR. So syntax is exactly same as AND or AND I. The only difference is you need to specify OR operation. So here you have source register, destination register. Their values will be OR together, and the result will be in the destination register. And you have another variant where you can specify the source as an operand instead of as a register or immediate. Bitwise logic exclusive OR, it has only one variant. You cannot specify the immediate operand. So both operands, the source and the destination, they should be loaded first into the registers, and then you can perform the exclusive OR operation between them, right? Then you have two other instructions they which take only one register. So one is the complement instruction. So when you say complement RD, so the content of the destination register will be complemented and put back into the destination register. And when we say complemented, it is one's complement, which basically mean that all the bits will be flipped. If it was initially 0, it will become 1. If it was 1, it will become 0, right? And negate, it is used to calculate to get the two's complement of a register. And you know what is two's complement. You simply first find the one's complement and that then add 1 to it, right? So source the whatever value you have in the destination register, it will be two's complemented and then put back into the RD itself. Any questions? Okay. So the AND instruction, we can use it to basically, it can be used for other purposes, but one widespread use is to clear the specific bits of a byte. So this operation is known as masking, right? So for example, let's say you have a value 0x2a, right? And what you want to do is that you want to get rid of the lower 4 bits. You want to set all of them as 0, but for the upper 4 bits, you want to keep them as it is. You want to keep them untouched, but for all the bits in index 0 to 3, you want to set them to 0. So what you can do is that you can do the AND I operation. So you load your value 2a into R20 and then you say F0. So when you say AND with F0, so when you say AND F with F0, so you get this thing actually. So this is your value 0x28 is value in your R20, and this is your mask. So when you say mask, it's basically mean that at all of them, we wanted all of them to set equal to 0, but however we want to keep them untouched. So for those bits which we want to keep untouched, uh, we in the other operand we have all the bits in the corresponding position set equal to 1, and for those bits which we want to set equal to 0 in the other operand, we have the corresponding set bits set equal to 0. So now when will you do the AND operation? So in the result, this is uh, these 4 bits are untouched, the most significant, and then the least significant 4 bits, they are set equal to 0, right? So this is known as masking because you are applying a mask and you are saying, okay, I want to set these specific bit equal to 0 and I don't want to touch a bit set at the specific position. So any bit which you don't want to touch, you simply in the mask, you set its the the value for the operand for that corresponding bit position equal to 1, and other bits which you want to set equal to 0, you put a value of 0 in the bit position of the second operand uh, equal to 0. The value of you put value of 0 in those bit positions. If it is not clear, please let me know. Okay, so you can use AND to clear the specific bits, and you can do the opposite of this exactly same thing by using the OR operation, which allows you to set the specific bits of a byte equal to 1, right? So here is actually the same, we have same operand 0x2a, and what we want to do is that we want to set all the bits in upper 4 bits equal to 1, and we don't want to touch the lower 4 bits, right? So what we can do is that those bits which we want to set equal to 1, we in the second operand we set the values equal to 1 in those corresponding bit position, and those which we don't want to touch, we set the value equal to 0. So here is like when you convert the number into binary. So 0x2a is like, I don't want to read the binary of the number. 0xf0 is this one, right? Now when you will do a OR operation, so basically what is happening, so remember in OR operation, if any one of the input is 1, output is 1. So that's why all these 4 bits are set equal to 1, and these lower bits, they are untouched. If the value in R20 was 0, the result is 0. If value was 1, output is 1, right? Any questions? So again, you can use the AND operation to clear specific bits, and you can use the OR operation to set the specific bits in the register. Okay. So other than those logic instructions, we also have some rotate instructions which are useful in some operations. For example, if you want to transmit the data of a register, or you want to send to the output the data of a register on a single output pin in a sequence. In a sequence mean you want to send the data bit by bit. So in those cases, you can use these rotate instructions, and there are there are various flavors. So rotate on right instruction, actually what it does is that it rotates the bits from left to right through the carry flag. So what happens is that carry flag enters the most significant bit of the register which you are specifying here, and the LSB exists to the carry flag. So here is like visual understanding of what is happening. If you have this register on which you want to perform the rotate on right instruction. So what happens that least significant bit, which is basically the bit at index 0, it will be placed into the carry, and the value of the carry, which it was like before doing the rotate operation, it will be moved into the most significant bit position of the register, which is the bit at index 7, right? So so C is moved to the most significant carry is moved to the most significant bit, and LSB is moved into the carry, right? So here is an example. Let's say here example where we are doing the rotate on write operation, or rotate on write instruction on this data, right? Or on this bit sequence, which basically mean we have this value in the register, right? So this value is basically equal to 0x26. So what we are saying is initially we are clearing the carry, right? So why we are clearing the carry? Because if let's say the carry initially had some number 1, that then what happened, that 1 will be moved into the most significant bit position, right? So whatever value previously you had in carry, that will be moved after first rotate into the most significant bit position of the register. So we are making it clear to be sure that what value we have in the carry flag. So now C is equal to 0, then you are loading 0x26 into R20 register, and now when you say rotate on right R20, so what happens that, remember, now this is the value you have, this is the value you have in R20. Now when you say rotate it on right, so this 0 will be moved into the carry, right? And all other bits, these bits will be moved one position towards right, and the older value of the carry will be placed in the most significant bit. What was the older value? 0, right? So this value is placed here basically, and this 0 has moved into the carry, right? Now, when you say, okay, rotate it on right again, so what will happen is like this bit, it will be moved into the carry position. So it becomes 1 into the carry flag, it becomes 1. And the older value of the carry is moved in the most significant bit position of the register. So basically, let me draw it like this just to not. So it comes here, right? Now, when you say rotate it on right once more, so then this one will be moved into the carry flag here. So it becomes 1, and this older carry, it moves into the most significant bit position of the uh, R20 register. So it becomes 1. The most significant bit becomes 1. Okay. And all the bits in between, they are moved one position toward right. Any questions? No? Okay. So here is another example. Uh, not another example, another instruction which actually does exactly the same thing but in the reverse direction. So it is rotate on left through the carry flag. So here what happened is that your most significant bit, it enters the carry flag, and value of the old value of the carry, it moves into the least significant bit of the register, right? So so here, uh, again, we are having a look at an example. where we are doing the rotate on left on a specific value. In this case, we are setting the carry flag initially equal to 1, right? And this is it is not like you must set the carry flag equal to 1 when you are using the rotate on left, and you must clear the carry flag when you are using rotate on right. It is just your choice. We just need to be sure what value we have initially in our carry flag, right? So we just want to be deterministic. So here we are putting we are setting carry flag equal to 1, and then we are loading the value of 0x15 in R20. So if you convert into the binary, you will have this number. Uh, you will have this number in R20. Now you are saying, sorry. Now you are saying rotate on left R20. So which basically mean that the most significant bit will now go into the carry. What is the most significant bit? This one, right? So it will go to the carry, and carry is set equal to 0. And your carry, it goes into the least significant position, right? So what was carry? Carry was original carry was 1, this one here, so, right? And it goes to the least significant position, and all other bits in between, they are moved one time to the left position. Then when you say, okay, rotate on left once again, so what happens is that your carry will again will move into the least significant bit position. So what was carry? This one here. And your most significant bit moves into the carry. So the most significant bit was this one, 0, right? So I don't want to draw it again, because then it will become like visually not understandable. So this 0 is placed into the carry here, right? And all other bits, these bits, they are moved once to the left position. So here it becomes, these two ones are moved on the left side, then you have 0 here, this one is moved here, this 0 is moved here, this one is moved here, and 0 is moved once onto the left, and then this 0, as we said, which is most significant bit, it goes to the carry here, right? Any questions here? I don't want to go to the other next to rotate on left instructions, but it is pretty clear how things are working here. If not clear, let me know. When would rotating the bits be helpful? Okay. Uh, Actually, when you want to, for example, send data in a serial way, like serial way mean, like let's say you have data in a register, like 8-bit register, but you want to send it not on 8 uh, output ports, you want to send it on a single output port, let's say with which you have connected some device, some serial device, which is like say which can take only 1 bit at a time, right? So then what you will do is that you will do these rotation operations to send the data uh, to the output bit by bit on a single line. Actually, in the syllabus document, I have mentioned which sections of the book are actually talking about these rotate instructions, and there they have examples of how these rotate left or rotate right instructions are used to, for example, send out the data bit by bit in serial way, or read the data serially from an single input line, and then pack it in an 8-bit register. So in both cases, whether you are reading the data, serial data, or you are writing the serial data, in both cases, you will need the rotate operations. I hope it answers the questions. If not, let me know. Okay. Uh, Okay, logical shift left instruction. So you may be like getting confused that why we have so many shift instructions. Like earlier we had rotate on right, then we had rotate on left, and now we are talking about logical shift left instructions. So these instructions, the difference is that these instructions, they actually involve carry. So, but rotate on left or rotate on right. But a logical shift instruction, it doesn't involve carry. There is no loop back from the carry, for example, into the least significant bit. There is no such loop. So that's the difference here. Let me just simply erase it so that you are not confused. Uh, okay. So it will, what it does is that it's every time when you say you want to shift a register, you want to perform a logical shift left instruction on a register. So on every execution of that instruction, zero is like filled in from the left side, but most significant bit goes to the carry, right? And what is the usage of this instruction? You can use this instruction. Uh, you can use this instruction to multiply numbers by 2, right? So you don't need to do the multiply instruction, because I don't know how many cycle it takes, but typically multiply instruction is more expensive in terms of clock cycle as compared to the logical shift instruction, right? So if you are multiplying a number with 2, so you don't need to use the multiply instruction, you can simply use the logical shift left instruction, right? How it results in multiplying a register value with 2, I will explain it, right? So, but for now, we are just focusing on that whenever you say logical shift left on a register, so the 0 is fed in from the least significant into the least significant bit. All other bits are moved to one place toward left, and the most significant bit goes into the carry flag, right? So LSL, or logical shift left, multiplies content of the register by 2 if the carry flag is not set afterwards, right? So what is meant by if the carry flag is not set afterwards, which means that if carry flag does not become equal to 1, because if carry flag becomes equal to 1, it's basically mean that we have multiplied the value of the register, and the result of the multiplication is big enough that it cannot be contained in 8 bits, and therefore the result is not correct, right? So here is an example. When you will see it by yourself, you will understand what I mean. So let's see what happens to this 8-bit value after running LSL instruction on the value 3 times, right? So let's say initially we are initially clearing the carry flag, uh, and then we are loading the value, which is a 0x26, which is simply hexadecimal form of the same bit pattern, into R20, right? And now when you say LSL R20, what will happen? So remember, most significant bit will go to the carry, and 0 will be placed into the least significant bit, and all other bits, they will be shifted 1 towards the left position, right? So uh, so this 0, it will go to the carry here, right? And oh, no, sorry, let me erase. Yeah, so when you are saying now uh, LSL R20, so what happens is that your 0 this 0 will be moved into the carry flag here, and this carry, for the older carry value, which was 0, is fed it in the least significant bit position here, right? And all other bits, they are moved, like all of these bits, right? They are moved to the left position, right? So now if you look at this binary, so it is basically uh, 32 in decimal, right? So after shifting it left once, now it becomes 76, which is basically you are multiplying 32 by 2, and it becomes 76, right? Sorry. When you do again the logical shift left on the same data, so what happens that this 0 will be again moved to the carry. So C is set equal to 0, and the older carry is moved into the least significant bit position here, and then then these 6 bits, they are all of them are moved once to the left position, right? So you get this 8-bit number. Now, when you convert this 8-bit number into the decimal form, you will see it is 152, which is basically 76 times 2 equal to 152, right? Remember, in all three cases, in all these two cases, not three, in all these two instructions, we have still C is equal to 0, right? Now, let's talk about the last iteration. So here, when you say again LSL R20, so what happens is you are saying put this C is equal to 0 into the least significant bit position. So we are putting it here. This C is equal to 0, right? And all these bits, they are moved once to the left position. So we have these 6 bits here, sorry, 7 bits here. And this most significant bit, it goes to the carry, right? Now, when you convert this binary number into the decimal, it is 48, which is not equal to 152 times 2, right? Why it is not? Because we actually, uh, we, we cannot contain the result of 152 times 2 in a 8-bit register because it is greater than 255. 255 is the maximum value we have in an 8-bit register. So, what when we say that LSL, it multiplies the content of register by 2, and this statement is true as long as the carry flag is not set, right? If carry flag is set, then the result is not equal to multiplying the original value of the register with 2. Any questions here? Okay. Okay, so uh, just like LSL, we have LSR instruction, which is logical shift right instruction. And again, this instruction, it actually, you can use it to achieve the division of a number by 2, but only for unsigned numbers, right? Uh, so if your number is unsigned and you are moving it right using the LSR instruction, you are effectively dividing it by 2, and carry flag will give you the remainder of your division result, right? And how it works, how it is different. Uh, this time your LSB is fed into the carry, and 0 is fed into the most significant bit position, right? So again, let's do another example. Where we have this number. Let me check what time it is. Yeah, okay, we still have time. So let's say we have same number, and this time we want to divide it by 2, but we can do that by using the LSR instruction, logical shift right instruction, right? So first we are loading the value in 0x26. We are loading the value 0x26 into R20, and so we have this bit pattern now in R20. Now when you say logical shift right, so what will happen is that your least significant bit, it will go into the carry, right? And 0 is fed into your most significant bit here, and all other bits, these 7 bits, they are moved once to the right position, right? So you get this value. Now, if you convert the original bit pattern into decimal form, you will see it has a value of 38. But when you convert the shifted bit pattern into the decimal value, it is 19. Now, so basically you are dividing 38 by 19. So, sorry, 38 by 2. So when you divide 38 by 2, the remainder is 0, right? Because 38 is an even number. So carry is telling you that remainder is 0. Okay, so carry always, in this case, will act as a remainder holder. Now, let's say when we do once more, we do the LSR operation. So this least significant bit, it goes to the carry, right? And most significant bit is filled with 0, and then the remaining 7 bits, these bits, they are shifted once toward the right position, and we get this pattern. So which is basically equal to 9 in decimal form, right? So when you divide 19 by 2, so you have quotient of 9 and you have remainder of 1, right? Because 19 is odd number. Again, when we do LSR once more, so this least significant bit becomes, it will be moved to the carry. All other bits are moved one position towards right, and most significant bit, it is set equal to 0. So which is when you convert into the binary form, decimal form, it is equal to 4. So basically you have divided 9 by 2. So the quotient is 4 and uh, your remainder is 1 because 9 is then again an odd number. Okay. Any questions? So actually LSL and LSR instructions, you can use them to multiply a number. So for example, you can use LSL to multiply a number with 2, and you can use LSR to divide a number by 2. But as long as both numbers are unsigned, and in case of LLS, as long as the carry is not set equal to 1. Because if once the carry is set equal to 1, it's mean the number is too big to be contained in an 8-bit register. The result of multiplication is too big to be contained in a 8-bit register. Okay, so we said that we can use the LSR instruction to divide a number by 2, but that is true for unsigned numbers. What about if we do we have a similar instruction which can divide a signed numbers? Yes. So that is an ASR instruction, or arithmetic shift right instruction. So how it is different? So the difference is the similarity is like from LSR, the similarity is that still LSB goes into C, into the carry flag. However, most significant bit, it is not filled with zeros. It is filled with whatever the original value, the MS. So basically, most significant bit always retains its value. Okay. So this instruction divides a signed number by 2. Okay. Uh, yeah, I'm not going to read this because I have explained how this instruction works. So now let's say we have a number, and we want to divide it by using the ASR instruction, right? So uh, this is incorrect, right? Let me fix this right now, because otherwise when I will load the slides, you will later be wondering what's happening here. So we should have here the same bit pattern, which is equal to 0xD0, right? So it should be 1 1 0 1 0 0 0 0, right? So the question is like, what happens to this bit pattern after running 5 ASR? So this bit pattern is equal to 0xD0, right? And 0xD0, if you like treat it as a signed number, so it is minus 48, right? Remember, the most significant bit in signed numbers is treated as a signed bit, so it has a negative weight, right? So now when we say arithmetic shift right on R20, so what happens that least significant bit is moved into carry here, and the most significant bit, it keeps its value as it is, and all these bits, 7 bits, they are moved to the right direction once, right? So, and as a result, you get this bit pattern. Now if you convert this bit pattern into the equivalent decimal form, you will find it is minus 24, which is basically half of 40 minus 48, right? And then the things go same for all other like ASR 20 instructions. I'm not going through them because it is pretty clear how things are working, right? Every time you are moving the least significant bit into the carry, and the most significant bit, it retains its value, and all other bits, they will be simply moved towards right direction one position. Mhm. Any questions? Okay. Okay, so let's talk about BCD, pack BCD, and ASCII conversion. So before talking about ASCII conversion, we first need to ask what is a binary coded decimal number. Uh, to relate, okay, uh, let's first talk about ASCII. So for example, when you are receiving any data, like let's say you are sending data from your keyboard on your computer to the AVR microcontroller, right? By reading the data through serial port. So whenever you press, let's say you press the key 0 on your keyboard, so an ASCII of 3030 will be generated, right? So when you convert this 30 into the binary form, you will get this pattern 011 and then four zeros. So remember that ASCII is 7-bit pattern, right? So that's why here we have 7 bits, not 8 bits, right? So a BCD code, now the BCD coding is a different way of coding the characters, right? So for example, when you say like you want to encode the character 0, what you do is that you simply create the 8-bit binary of that number. Instead of saying that when you press 0, an ASCII code of 30 will be generated, and then you will have the 7-bit binary of that ASCII code. So what you are doing basically that for each character, each number like 0 up to 9, you are creating an 8-bit binary, right? Like here you have 8-bit binary of 0, 8-bit binary of 1, 2, and so on up to 8-bit binary of 9, right? So uh, so the thing is that there are some components in the system which basically use still the BCD coding for coding the numbers. They don't use the ASCII coding, right? But then there are some other components which, for example, keyboard, which use the ASCII coding, right? So if we want to translate the data between like a component which uses the ASCII code and a component which uses the BCD code, so we need to do the translation, right? So let's say this is I'm simply saying component 1, and you have, and here you have component 2. And let's say component 1 uses ASCII coding to encode the data. So basically, if you want if it want to send a value of 0 to component 2, then it will send this binary, right? But this component 2 don't understand this binary coding, right? It expects the BCD coding. So which means that in between we need to we need to do the translation from ASCII code to the binary code. And that is also true if C2 is sending data back to C1. So in that case, we will need to translate BCD coding of numbers back into the ASCII coding, right? So uh, So, uh, BCD codes, they have two variants, packed or unpacked. Unpacked version is the one where we use 8 bits to represent one number. Like for example, in all of these are the unpacked BCD codes of numbers from 0 to 9, right? But uh, so basically, if now let's say if I want to have the BCD code of let's say 49, let's say in hexa. So what I will do is that I first need to uh, uh, first I need to not in hexa, in 49 in decimal. So first I need to do 8 bits to generate the BCD code of 9. So which will be, let's say this one. I don't want to write it. It is already here, right? And then I will need another 8 bits to generate the BCD code of 4, which will be this one here. So it's mean that I will need 2 bytes to generate the BCD code to represent number 49, because each digit takes 8 bits, right? So this is actually like kind of wasting of memory. So what we can do is that we can use the packed version of the BCD code, where what we do is that we use the lower 4 bits to represent one digit and the upper 4 bits to represent another digit. So basically it's mean that in the packed version I will have only 8 bits, and like I will use lower 8 bits to represent the BCD code of 9, and then the upper 4 bits to represent the BCD of code of 4, which is 0010. So now this time I'm using only 1 byte to represent 2 digits in BCD coding. So this is like more like it will save the memory space, right? Any questions here? Okay, so how we can convert numbers from packed BCD form to the ASCII form? So to do that conversion, what we need to do is that we will first convert the packed BCD number into unpacked BCD form, right? And then once we have that number in unpacked BCD form, we can simply tag with it 011 to convert it into the ASCII form. So let's have a look, right? So let's say we have this packed BCD number 1001 and 0010, which is basically this is 9 and this is 2. So this is the BCD code for 92. Okay, for decimal number 92, this is BCD coding, right? So first we need to unpack it. Unpack mean we will use 8 bits to for the BCD code of 9 and then 8 bits to represent the BCD code of digit 2, right? So here we have the 8-bit unpacked BCD of digit 2, and this is 8-bit BCD code of digit 9, right? So once we are done with that, we simply need to tag with the unpacked BC file 011, right? So we simply need to add it, right? So which so you need to add only this number 0110 to the unpacked BCD form. So here basically what I'm doing is 0 0 1 1 0 0 0 0. I'm adding them, right? Adding it with the unpacked BCD form of 9. So when I will unpack when I will add it, so I will get this result, right? And then I'm also doing same thing with the unpacked BCD code of digit 2. So when I will do this addition, I will get 00110010, which is basically ASCII of this is ASCII of 2 and this is ASCII of 9. Okay, so this is how you can convert how you can convert the BCD packed BCD into the ASCII form, right? Uh, what about reverse conversion, which is basically from ASCII to the packed BCD form? It should be straightforward, right? So what you need to do is that you simply need to mask the upper 4 bits. So you simply need to set the upper 4 bits equal to 0 and keep the lower 4 bits as it is. So what does it mean? You can simply do the AND operation with the ASCII value of the number. So let's try to do it quickly here. Let's say I'm taking the ASCII value of 2, 0 0 1 1 0 0 1 0. So first I need to do what I want to do. I want to set all these 4 bits, upper 4 bits equal to 0 and keep the lower 4 bits as it is. So I can AND it with a value of, if I'm reading from the most significant side, 4 zeros and 4 ones, right? So basically I can load this one, let's say into a register R20, and then I can use the AND immediate, right? And what will be this number in hexadecimal form? It will be 0xF, 0x0F, right? So I can say AND immediate R20 0x0F. So what will I get then? After AND operation, I will get 0, 1, 0, 0, and then 0, 0, 0, 0. What is this? This is unpacked form of digit 2, right? This one exactly same, right? Hmm. Now, let's say I want to convert, I want to like pack the two uh, uh, I want to pack two BCD values in a single byte. So I'm not going to like convert this ASCII of 9. I'm not going to show how to convert it because you need to do exactly the same thing. You simply need to do AND operation with 0x0F, right? And you will get again this one. So let's say I get here the unpack value of 0, 0, 0, 0 and 1 0 0 1, right? Let me check the time before we still have 5 minutes. Okay, so now I need to what I need to do is, but they are taking 2 bytes, right? 1 byte for 2 and 1 byte for the digit 9, right? So how can I pack them together? So for packing, what I can do is that there is an instruction which we have not covered in the slides. So what it does is that it swaps the lower 4 bits with the upper 4 bits. So for example, let's say I have this value in register, let's say I'm simply saying R21, right? So when I say swap R21, what will happen? That after executing this instruction, lower 4 bytes will be swapped with the upper 4 bytes. So it will become 1, 0, 0, 1, 0, 0, 0, 0, right? So in RT2, now I have this one, R21, I have this one, and in R20, I have this number, right? And now if I simply say R21 and R20, I'm not going to write it. Do you want, let me write it then. R21 and R20. So what will you have? If you have R20 is this one and R20 is this one, when you will do OR operation, so you will get 0, 1, 0, 0, and then 1, 0, 0, 1, which is backed, which is again packed BCD form of 92. Okay. Someone sent a message. And instruction used for adding. Yeah, for adding in the sense that you can set the bits equal to 1, 1, right? You can set the specific bits uh, equal to value of 1. Yeah. Any questions? No? Okay. If no questions, then that's it for now. Okay, one question before we leave. Not question, but I mean, I was expecting you to ask this question, and I think later you will send me an email that what is the syllabus for the midterm exam, right? Uh, so let me, how can I? So, okay, so whatever we have covered until today, right? Which is 10/07/2025. So all those slides are included in the syllabus of midterm 1 exam. Okay. So you are responsible for everything since start of the semester to today. Okay, if there are no questions, then that's it for now, and see you on Thursday then.